but instead of Br, we have R. And there's the product. So here's some examples. Chloroethane, benzene, room temperature, aluminum trichloride. Out comes ethyl benzene. And of course the other product is HCl, that and that. Intramolecular case, since we have carbon-carbon bond forming reactions, we can use this to cyclize compounds. So this electrophilic carbon attacks selectively here because it can't reach anywhere else. And so we use aluminum chloride again. I'm giving you often in these reaction schemes solvents and additional conditions. Don't have to memorize that. It's just to give you an idea of the cooking details when you actually do this in the labs. So in this particular case, they use carbon disulfide. That's the sulfur analog of carbon dioxide, which is actually a liquid and acts as a solvent. And as you can imagine, it's a super polar solvent because it's got carbon with double bonds to both sides and sulfur. So it's very polar and it dissolves everything, including the aluminum chloride. Or nitromethane is another good solvent, also very polar. Room temperature, and out comes the cyclized compound. Now you notice the yields are not great. 28 is very iffy, and 31 is also, it's very iffy. You really like to have at least 70 to 80% to be reasonable. Okay? And the question is why? And the answer is that unlike halogenation or nitration or sulfonation, where the products, the substituted benzenes, are less reactive than the starting unsubstituted benzene because all the new substituents are electron withdrawing, making that benzene relatively electron poor and therefore a worse nucleophile. Introducing an alkyl group does exactly the opposite. Alkyl groups are pushers. Right? So the product benzene ring is actually more electron rich than the starting benzene. And so in competition, particularly as this guy builds up in our ocean of starting materials, it will compete for the activated chloroethane with benzene. In other words, you get overalkylation. The product reacts further, you get diethyl, triethyl, tetraethyl, and so forth. And there's another reason in many of these reactions, because the Lewis acid activation generates a strongly delta plus carbon, which in the case, and we've only seen primary carbon so far, so there's no dissociation, full dissociation, because primary carbocations are no good. If this were secondary, or tertiary even, carbon, you would get the full salt of carbocation plus the aluminum tetrachloride anion. Okay, so it forms the full carbocationic species. Carbocations have problems, right? Chapter 7, hydride shifts, carbon shifts. And there's another problem of polymerization if there are alkenes around. Okay? So that leads to product mixtures if the alkyl group has a chance to do hydride shifts and carbon shifts. And that also often reduces the yield. So here are different starting materials, all of which do exactly the same chemistry. What you basically need is an alkyl group with a leaving group that can form a carbocationic intermediate, or you can use a double bond as a precursor to a carbocation. All of these work in the Friedel-Crafts alkylation. Okay? So in the case of this secondary alcohol, you can use any Lewis acid. These guys just use BF3. You could have used aluminum trichloride if you wanted to, or FeBr3. It doesn't matter. All of those will attack the oxygen instantly and make this a good leaving group. It will leave to make the carbocation. The carbocation will attack to do the electrophilic aromatic substitution. Starting from a double bond, all you need is acid, actually. In this case, these guys used HF. You could have used something else, some other acid, sulfuric acid. Dilute sulfuric acid, because you're protonating, you get a secondary carbocation, which in the presence of the benzene ring will undergo electrophilic aromatic substitution. Okay. So the problem is the overalkylation and the rearrangement chemistry. And fortunately, there is a way around that. And that is the second part of the Friedel-Crafts reactivity, namely Friedel-Crafts acylation. In acylation, instead of an alkyl, we use an alkanoyl reagent, and namely the corresponding alkanoyl halide compared to the alkyl halide. Okay? So alkanoyl halides, we shall learn, are derived from carboxylic acids. You can buy them or make them in the lab readily. And these guys with the Lewis acid generate the equivalent of RCO+, which undergoes electrophilic aromatic substitution to generate the alkanoyl benzene. Now what's the ketone? And that guy is, because it bears a carbonyl function that can, by resonance, withdraw electron density from the benzene ring, that generates a benzene ring that's much less electron rich than this one, so there's no competition. Okay? The product is less reactive than the starting benzene. Moreover, since we have a carbonyl function here, and the intermediate carbocation is, as we shall see, RCO+, there's no rearrangement possible. That carbocation is a very special carbocation called acylamine, and so rearrangement is not possible for these kinds of compounds. And that improves on the yields. So a typical example is this: acetyl chloride and benzene, aluminum trichloride as the activator. You work it up with acidic water, out comes the ketone in quite reasonable yields. An equivalent to an acyl halide is an anhydride, where instead of as a leaving group, the leaving group being halide, like chloride, it's actually a carboxylate. So in this case, it would be acetic anhydride. The right half of the molecule acts as a leaving group. The other half acts as an acetylating agent. And so you get the same reaction as shown up here. We won't deal with those right now. We'll come back to them when we talk about carboxylic acids. So what's the mechanism here? That's a little bit of a weird one. We start with an acyl halide, and what we really want is generate this guy, the aluminum, and this is indeed the crucial intermediate, complexing to X and then pulling on the X to generate this so-called acylium cation, which is the hot electrophilic species. A very unusual carbocation. Actually, it forms relatively easily because it's stabilized by resonance. But for electronic reasons, namely reasons of resonance, all carboxylic acid type derivatives get attacked by electrophiles much faster on oxygen. And the reason is that this oxygen, these lone pairs are much more basic, because when you attack them, you generate a species that can have resonance. Resonance involving these electron pairs on the X. Okay? So the initial reaction is aluminum immediately docking onto this oxygen. Okay? But this is reversible. Okay? And every now and then it will jump down to make the intermediate that leads, that's active in product formation. And so the X is pulled off, and you get the acylamine. Okay? Two resonance forms. Here's the leaving group. Again, this is completely analogous to what we did for bromine. The Lewis acid comes in and rips off the halogen. In the case of bromine and chlorine, it's 1/2 of the reagent, leaving behind a positively charged electrophilic species. And in this case, the acylium ion then attacks, and you get the usual intermediate, proton comes off, and you get the corresponding acyl system. So the way around the Friedel-Crafts alkylation over alkylation is to use Friedel-Crafts acylation. There's another trick you can play in Friedel-Crafts alkylation to avoid over alkylation. And that is when your starting material is cheap, and in this case it's just benzene, so that's dirt cheap. It's used as a solvent, sold in ton quantities. You can just use huge excess of benzene, actually use benzene as a solvent, and just add one equivalent of the alkyl halide. Here now, when the product is formed, it's surrounded by an ocean of starting material benzene. So the reagent can't see the forest for the trees sort of thing, or the other way around. It can't see the product. They're swamped out in the large excess of benzene, so we'll always react with benzene rather than product molecules. And then you finish your reaction, you distill off your excess benzene, and you get a good yield of the alkyl product. But later on, we'll see we'll have very expensive functionalized benzene rings. In complex synthesis, your benzene may be embedded in some polycyclic frame, and it will be expensive material. You can't use that in large excess. So it's better to then resort to the Friedel-Crafts acylation. And here's, again, an electrostatic potential map of an acylium cation, in this case the acetyl cation. And again, it looks like nitronium, deep blue, very hot carbon. You can see the electron density, the plus charge, being primarily on carbon. A little bit on oxygen because of this resonance structure here. So the oxygen, even though it has an electron pair, is green rather than red because of the plus charge. So there's a little twist that you don't have to remember, but you should keep in mind. In the Friedel-Crafts acylation, we need to use stoichiometric amount of what ostensibly is a catalyst. And the reason for that is that the Lewis acid is used up by complexation to the product ketone. That electron pair is sufficiently basic, or to put it differently, the electron sextet aluminum is sufficiently Lewis acidic that it will dock and basically take the aluminum chloride out of circulation. So typically people use 1.1 equivalents or so, a slight excess of aluminum trichloride in the Friedel-Crafts acylation. Once you're done, you dump in water, and all of this falls apart, and the aluminum chloride is hydrolyzed to aluminum hydroxide. And so everything disappears, and you liberate your ligand. You don't have to state so in a synthetic scheme. Just writing aluminum chloride is fine, but it's understood that you actually, even though it is a catalyst in the actual mechanism, it is actually, because it winds up on the product, docked to the product, it's used with stoichiometric amounts. So there's synthetic take-home lessons of this kind of chemistry. We're introducing functional groups. Functional groups allow you to do chemistry. And I already said that if you halogenate a benzene, that halogen gives you a handle to make Grignard reagents, phenylithium reagents, and those, of course, you can react with carbonyl compounds and the like. So you can introduce alkyl groups that way also. Acyl benzenes, of course, have a carbonyl function. That has rich chemistry. We already know some of it. Basically, reduction with soda borohydride from chapter 8 and attack by Grignard reagents and alkyl lithium reagents, so you can make carbon-carbon bonds to this carbon. And we'll learn much more about that in chapter 17. And then next week, we'll see how to use the nitro and sulfonyl functions. So that's all I wanted to say today. Have a nice weekend. Enjoy the weather.